algorithm can be used both for regression and for classification, and that is the case of decision trees. So decision trees are extremely powerful, and also unlike many other algorithms, they do not require you to standardize or normalize your data. So let's look at how they work. So decision trees are supervised learning algorithm, and the principle is relatively simple. Imagine that we have this data set here on the left with three classes. We have gastropod, we have bivalves, and we have quartz crystals. What you do in a decision tree is you ask a question, and that question could be, is the chemistry of this particular sample that you take silica? And you will see that we have different things that we use. We have a Gini number that we'll talk about. We have the number of samples, we have different values, and we have the class. So what is the Gini number? Well, the Gini number is essentially known as the purity of the branch of the tree. So Gini is 1 minus the sum of the probability of finding a class squared. This sounds a little bit complicated, but really the principle is relatively simple, and Gini is essential for understanding how decision tree works. So let's look at an example from this first branch. Why is Gini 0.66 here? So we have 10 samples, and the value of those samples are 3 because we have 3 quartz crystal, 3 because we have 3 bivalves, and 4 because we have 4 gastropods. So we can simply calculate the Gini now using this equation as 1 minus 3 over 10 square minus 3 over 10 square minus 4 over 10 square, which is equal to 0.66. And that is simply a function of how many item or instances of a particular class you have in this particular branch of the tree at that particular time over the total number of samples. And if you think about it, this number is a function of the purity of that particular leaf. And we'll see why in a second. So now, how does a decision tree make a decision? How does it actually split the data? Well, for that it uses an equation known as the CART equation, which is very simple. The CART equation, or that cost function if you want, tries to reduce the number of sample on the left side of the tree over the total number of samples times the Gini number of the left side plus the number of sample on the right side of the tree over the total number of sample times the Gini number of the right. So in other words, it's going to divide the tree into two branches, a left branch and a right branch. So now we're going to look at the left side of that decision tree. And because the question is whether the mineralogy is silica, there's only one class that fulfills that requirement, which is basically the quartz. And so that means that the Gini number of that particular class now is 0. That particular branch is 0. Why? Because if you look at it, we have 1 minus 3, that's a 3 quartz, over 3 it's 1, so the whole thing comes to 0, and all the other terms are equal to 0. And when the Gini number is at 0, the branch is said to be pure, and this is known as a leaf node where we have just one class in an idealized situation. So it's the lowest number you can get with the Gini equation. Now the other side of the tree, which is false, is not as pure because we have both the gastropod and the bivalves in that particular class. So what's the Gini number? Well, if you do the math, the Gini number comes down to 0.4898. And of course you can continue dividing this particular branch, because this is not a leaf node, further and further on using the same CART equation. And you can ask another question. So in this case, I said, is the weight less than 10 grams? And just for argument's sake, I'll say that if it's true, most of the samples falling in that class are actually bivalves. So we have 3 samples, 2 are bivalves, 1 is a gastropod. And when it's false, we have 4 samples, 1 is a bivalve, and 3 are gastropods. So these two classes are not completely pure, so they don't have Gini numbers of 0. In fact, the left side has a Gini number of 0.4444, whereas the right side has a Gini number of 0.375, and you can do the math if you want to convince yourself that this is true. But you don't have to have completely pure leaf node to stop dividing them. In fact, that is one of the hyperparameters of decision tree. It is to decide when to stop to divide. So what's the depth of the tree? Now you can use decision tree for classification, but you can use the same decision tree also for regression. The trick for regression is you replace the classes by numbers, and then you basically bin the numbers together and you try to reduce the difference between the different numbers to get to the number that is the closest to what you're trying to predict. But the principle is the same. Decision trees are very powerful and they're very useful, but they do have their limitations. One of them is they tend to overfit the data very easily, and the one hyperparameter you can control is precisely the depth of the tree. If you do a lot of different depths, so if you say you can go down to 10 or 20, 30, whatever the data set size that you have, that number will be different. But if you give too much depth, you will overfit the data. So be careful about this. The other problem with decision trees is that their decision boundary tend to be orthogonal. So it doesn't always work with every type of data. So that's one of the problems. And something that's more subtle is they tend to be eager at reaching a solution. So at each branch of the tree, you will split at a Gini number using the Carr equation that is ideal for that particular node, but it may not be ideal for the entire tree. And we'll see later that we can overcome this with another algorithm known as random forest.